Hello everyone, welcome back to Physics 331. Today what I want to talk about are Fourier transforms, and so it's going to be a way to go back and forth between the time dependence and the frequency content of signals that are not periodic in time. And so let's just think about what we've learned so far about the Fourier series. The Fourier series allowed us to take a periodic function, so they work well for periodic functions. And if, for example, we knew the time dependence of some periodic function, so some f of t, and suppose it was a square wave that's periodic, and we call the period 2 times t, then what the Fourier series allowed us to do was to work out the coefficients of the terms of different frequency in the series. And so we would have our coefficient Cn, and there would be, for this example of a square wave, there would be a spike at a frequency of 1 over 2t. So this would be the fundamental frequency. And then we would have all of the odd multiples of that. So we could go to 3 times 2 over t, and we could go to 5 times 2 over t, and 7 times 2 over t. And what we found is that in this specific example, the amplitudes of these coefficients decreased as we went to higher and higher frequency, to the higher and higher harmonics. I haven't drawn it, but we would also have the negative n value. So we'd have a c minus 1, which would be at a frequency of minus 1 over 2t, and so on. Okay, so let's just make some observations about this. Observations. One observation is that the periodic functions are made up of discrete frequency components. Right, and so our frequency components of the square wave are at 1 over 2t, 3 over 2t, 5 over 2t, 7 over 2t, and so on. Just looking ahead, what we will find is that when we think of non-periodic functions, like a little signal that pulses in time, that the frequency spectrum is going to be continuous. There'll be a continuous range of frequencies that are needed to compose that signal. And the other thing that we're going to find is that the other observation we can make about what we know about Fourier series is that the spacing between frequency components decreases as t increases. If we just look at this example here, the frequencies are proportional to 1 over t. And so as we increase t, the spacing between those discrete values gets smaller and smaller. And so if we think of like a pulse in time that's not periodic, we might think of that as having a period of infinity. And so then the spacing between these frequency components becomes really small, and we're going to get this, as we said, continuous spectrum of frequencies. Okay, so that is the goal. We want to generalize this analysis that we've done so that we can examine the frequency profile, or the frequency content, if you like, of some signal f of t that is not periodic. And so we'll draw an example of that. So, for example, let's suppose that we have some f of t that is 0 for all times, or all absolute values of time that are greater than some capital T. And so what would that look like? So we might have something like f of t, and here's our time axis, and maybe our pulse, whatever it is 0 in some range, and then it pulses up and it has whatever shape you like, and then goes down to 0. And so what we can do is we can identify some value of minus capital T and some value of plus capital T, where when we're between these two times, the pulse can be non-zero, but when we're outside this range of times, the pulse is 0. And so the way I've drawn it here, I guess our 0 in time would be in between those two. Okay, so what we want to do is we want to make use of what we know about the Fourier series, and that works for periodic functions. So we're just going to take this f of t that we've drawn, and we're going to make it periodic. So we're going to force it to be periodic. So we're now going to take some capital F subscript t of t, and we're going to say that's equal to our pulsed function, little f of t, on the interval minus capital T to t. And we're going to make f of t periodic on 2t. Okay, so like we've always been doing, we're going to use 2t as the period. And so what does that look like? So we're going to have big F subscript t. And what we'll do is we'll say, okay, in here was our original function, and that is going to be sitting between minus t and plus t. So that's our little f of t. And what we're going to do is we're just going to repeat that. And so let's see how well I can repeat that. And so over here, and it would just keep going on and on and on. Okay, and so this time over here would be minus 3t. This time over here would be plus 3t, and this is our time axis. Okay, good. So then what we can do is we can say, for the time interval between minus capital T and plus capital T, our original function, little f of t, is equal to the periodic function. And because this big F function is periodic, we can express it as a Fourier series, and we know how to do that. We sum from n equals minus infinity to plus infinity, and then there's some Cn coefficients. I'm going to put in some explicit dependence on t, which 2t, remember, is the period. And then we have e to the I n omega t, but remember omega is 2 pi over the period, and the period was 2t, and so that's pi over t. And so this would be n pi over big T times t. Okay, so that was the Fourier series in terms of complex exponentials that we worked out. And so what we needed to do, remember, was to have a way of calculating the Cn coefficients. And so we worked out how we could do that. It's 1 over 2t, the integral from minus t to t of the periodic function times e to the minus in omega t, and then we could write omega as pi over big T times t dt. Okay, so now is our first little trick here, is I want to manipulate this integral that we use to find the coefficients. And what we're going to do is we're first going to, we'll have the 1 over 2t out front, we'll have an integration, but then I'm going to say on this integration limit from minus t to plus t, the periodic function capital F is equal to the little pulsed function little f of t, and then I'll write minus in pi over capital T times t dt. And then the next thing I'm going to do is I'm going to say, well, because this little f of t is 0 outside of the range minus capital T to plus capital T, I can extend the integration limits to be from minus infinity to plus infinity. And this works since f of t is equal to 0 for values of, the absolute value of little t is greater than or equal to capital T. Okay? i.e. f of t vanishes outside of the time interval from minus t to capital T. Okay, good. So the next thing we'll do is we'll just say we'll start talking about like the nth frequency component. The nth frequency is omega n is equal to so omega, remember, is 2 pi over 2t, so that would be a pi over t would be the fundamental frequency, and then the nth frequency is n times that. Okay, and so we could also talk about the spacing between the frequency components, right? So remember way back in this picture, like we could talk about the spacing between the discrete frequencies. And so in this case, we would just take the difference, 3 over 2t minus 1 over 2t. So let's do that and say, therefore, the frequency spacing is the nth plus 1 frequency minus the nth frequency. And so we'll define that as delta omega. And that's just going to be equal to pi over t. And so we have over here like some 1 over t, 1 over the capital T in this coefficient. And so what we could start to do is we could say, well, let's see, that allows us to write, remember what we're calculating are the Cn coefficients. Cn of t is equal to 1 over 2t, but we could write 1 over t as delta omega over pi, so it's delta omega over 2 pi. Okay, and then the integral from minus infinity to plus infinity, and then we'll have f of t times e to the minus I, and then we have n pi divided by t, which is just this omega n, the nth frequency component. And so what we're going to have is an omega n times t, and then we are integrating over time. Okay, so something that we're going to make use of in just a moment here is that this integral is going to be be defined as this f hat of omega n. So notice if you were to actually evaluate this integral, you're going to integrate over time, and so all the time dependence inside the integrand will vanish, and you'll have something that just depends on omega n. So evaluating this integral of a function of time with respect to time is going to leave us with a function of omega n. So it's a way of converting from a time domain picture to a frequency domain picture, and that's the essence of Fourier transforms. Okay, so in this notation then, we could say that Cn of t is therefore equal to, what do we have? We have a 1 over 2 pi out front. The integral we're going to identify as, we just called it f hat, so that represents that integral over time. And then there's still a delta omega that's left over. Okay, good. So we're in fact almost done what we need to do. We've expressed these coefficients of the Fourier series in some way that might be convenient for us. And so all we're going to do is we're going to go back to this expression here and write down the Fourier series. So we have a sum over n, and we now have a new way of writing these coefficients, and then we have to multiply by this exponential. Okay, and we'll write n pi over t as this omega n that we had. So then returning to star, we have, let's see, on the time interval from minus t to plus t, we said that our pulsed function of time is equal to the periodic function that we constructed. That periodic function can be written as a Fourier series, and so we sum from n equals minus infinity to infinity, and then we have the Cn. But the Cn has a 1 over 2 pi, I'll put that outside of the sum, and then it has an f hat of omega n, which represents that integral of time that we had. We were going to multiply by e to the I think it was n pi over t, which we're going to represent as omega n, and then t. And then we have a delta omega from our Cn coefficient. Okay, so what we're going to do now is we're going to say, well, we've constructed this periodic function, but what if we made the period really long, like we take the limit that this period goes to infinity? Then what we're going to do is we're going to spread out how often, or we're going to increase the time that it takes for this function to repeat. And if we take the limit that the period goes to infinity, then we never have that repetition, and we're just left with our original pulse in time. Okay, so in the limit that we take t to infinity, what's going to happen? Well, the delta omegas that we calculated is in this red circle, and if t goes to infinity, sorry, it's not. Delta omega is, sorry, I got confused. Delta omega is here. So delta omega is the spacing of adjacent frequency spikes in the Fourier series. And so if we take t goes to infinity, that spacing goes to 0. If the spacing between adjacent frequencies vanishes, then the omega n in the red circle goes from being discrete spikes to a continuous function. So those are our two observations. So the first one is that the delta omega spacing becomes infinitesimally small. And that means that the discrete omega n becomes continuous. And if it becomes continuous, we'll just drop the n subscript and just call the frequency omega. Okay. And then if you look at this sum that we have, if the delta omega becomes infinitesimally small, omega n becomes a continuous variable, then this sum becomes an integral. And so let's say this is number sign. And so the second important observation is that the sum in number sign becomes an integral. Okay, and so let's write that sum as an integral. We have f of t, our function of time, is, there's still a 1 over 2 pi. The sum becomes an integral. And then we have f hat of omega n, but omega has become a continuous variable. And then we had e to the I omega nt, so omega becomes a continuous variable. Delta omega becomes infinitesimal, so we'll write that as d omega. So this is called the, so f of t is the inverse Fourier transform of f hat of omega. F of t is the inverse Fourier transform of f hat of omega. So this allows us to go from a function of frequency to calculate a function of time. So this takes us from, let's say, converts a function of omega to a function of time. That's the inverse Fourier transform. In fact, we've already worked out the Fourier transform, and it's this thing underneath the curly bracket. So f hat of omega in the continuous limit, f hat of omega is equal to, so the way we defined it, there's no prefactor in front of the integral. It's just the integral of f of t e to the minus I omega t. So it's the integral from minus infinity to plus infinity of f of t e to the minus I omega t. And this is going to be an integral over time. So f hat of omega is the Fourier transform of f of t. So it converts the function of time to a function of frequency. Okay, good. So I know that's all a little bit abstract, the way that we've done it, but that's where I'm going to stop for this video. And what we'll do is we'll try to make this more concrete in the next video by taking up some examples to see how we can actually apply this to some real functions of time and frequency. Okay, good. Thank you very much, and we'll talk to you next time.